afternoon we have two speakers. So Moisés Pinto from the University of Lisbon, from the Institute Superior Técnico, and José Gomes, that is from the University of Aveiro, is also a researcher at the CISECO, and both of them will speak about gas absorption by porous materials in different perspectives, but I will let them to introduce themselves about this. Thank you very much.
Thank you, Paula. So I will present the first part. I hope you like this short introduction on gas absorption, and also a little bit about how can we use gas absorption to characterize porous materials. Okay. Of course, the objective of this session will not be to turn you into experts on the field, but at least for you to understand what are the tools that we can use here to characterize the porous materials. Okay, so in the context of this course, yes. So
this will be an interactive class. Okay, so probably the very first slides, Moisés will present some theoretical aspects and some from an experimental point of view, but then we will continue the class with some hands-on exercises. Okay, so please switch on your computers. The session was prepared for Windows users. Okay. It is not very difficult to install the software in Linux systems, but since we don't hold any Mac-based computer, we don't know very well how to install these codes, but it should work in any computer, okay? So since this is an interactive class, just to understand if things will work well. Good afternoon.
We're alive.
So let me. Okay. This did not change. Yeah. Okay. Change first here. So first, it's just to introduce what is the concept of adsorption. So adsorption, from the conceptual point of view, is the increasing concentration of molecules near the interface. Near the interface, of course, when you have two different phases. Yes? So you can have adsorption in gas solid interface. We will focus on this. But of course there is also adsorption in gas liquid interface, in liquid liquid interface, and in liquid solid interface. Okay? So we will focus on one aspect. Let's say one type of adsorption, which is in the gas-solid interface. Nevertheless, it's just to highlight that there are these types of different types of adsorption. Yes? So, in the case of solids, it corresponds to the increase in the concentration at the surface of the solid. In relation to what? In relation to the bulk of the gas. Okay? So, molecules tend to accumulate at the interface. We will try to explain why, from the fundamental point of view, this happens. Okay? At this point, it's important to stress that this is more relevant in solids with high specific areas. So, solids that have very high surface areas. Why? Well, because in solids where you have low surface areas, it also occurs, but the extent is much less significant. So the cases we will highlight here is the cases where adsorption is so relevant that you cannot, how to say, properly describe the solid if you don't consider this adsorption phenomena. It depends on the porosity of the solid. But from the conceptual point of view, you have adsorption everywhere here where you look. You have a solid, you have a gas, you have most probably accumulation of more molecules at the interface, whatever interface you have. Okay? So let's continue. There are two types we can categorize in two different types of adsorption. So the physical adsorption and the chemical adsorption. The physical adsorption is when you have attractive forces between surface and molecules that are not very specific, let's call it this way. So it does not, how to say, have a reaction like in the case here below. So it always occurs to a greater or lesser extent. There is always physical adsorption, because this, as we'll see, is related to the nature of molecules and atoms themselves. They tend to attract each other, so physical adsorption always occurs. Chemical adsorption may occur or not. It's non-specific. There are non-specific interactions in here that play a very important role, so dispersive forces. There are specific interactions like coulombic, dipolar, and so on, that also play a role in here. It decreases with temperature, so if you increase temperature, you are unfavoring the adsorption. And from the technological point of view, for many engineering applications, we can use this, for instance, to regenerate the material. And you will see also in here it's very important when, from the experimental point of view, you want to measure adsorption in a solid. The first thing is to remove all things that are absorbed inside. So one strategy is to increase the temperature. Usually we talk about physical adsorption when we have interactions energies, so adsorption energies below 100 kilojoules per volt. This, of course, is a rough estimation. We can always discuss a little bit afterwards if we have time. The difference for chemical adsorption, I think, will be now more obvious. So in the chemical adsorption, we have a formation of a chemical bond on the surface, at the surface. So the molecule goes to the surface, and some type of bond needs to happen. So it's a reaction, let's call it. Okay? May not occur, so the chemical adsorption may occur or not, in contrast with what happens with physical adsorption. It depends, of course, on the chemical nature of the gas and the chemical nature of the surface. If you don't have groups in the molecule or at the surface that may react, it may not occur. So it only occurs at the first layer of the adsorbed molecules. So if it is a reaction, the layer reacts, the first layer reacts to the surface, and the second and third layer of molecules that are left to the surface don't have more groups to react, okay? It may or may not increase with temperature, so it depends on the nature of the reaction you have. You know, there are reactions that are favored with temperature, and there are reactions that are unfavored with temperature. And it is always a very specific interaction. It's a reaction. It's chemistry, okay? And adsorption energies usually are above 100 kilojoules per mole. Again, I stress yes, these values are rough estimations. So when we are characterizing adsorbent materials, so porous materials that have a very high specific surface areas that have quite a lot of porosity, we can characterize the materials in terms of particle size, granular adsorbents, if they are powders or beads or extrudates. We can characterize the porosity of the material. We will going to focus in here on how we can characterize the porosity of the material using adsorption. And of course, there are also the surface chemistry that can also play a very important role. So you have superficial groups, acidity and basicity of these groups. You have also surface stability. Okay, just to name a few. So we are going to focus in here, in this middle part. Okay.
The main issue here with the chemical problem is that these are aspects that are more difficult to analyze. Okay, they will require more extensive analysis, either from an experimental or from the computational point of view, and for the sake of time and simplicity. Yeah, we will focus just in this time.
So I hope that at the end of the day, we will have already a good idea of what is pore volume, specific surface area, internal area, external area, and pore size distribution. Yes? Using different techniques, either experimental techniques like solid or computational approaches. So the molecules, like I said, accumulate at the solid gas interface. So porous solids have a significant higher absorption potential, so we have interaction energy with the molecules. Yes. That goes to the surface. This is what we call the absorption potential, because each molecule can interact effectively with a large area of the solid. Yes, sometimes when you have pores, the pores we are talking about are pores that are on the same range of molecular size. Yes. So if you have a pore that is going, if you have a molecule that goes inside this pore, the molecule feels the potential of several walls. Yes? Of course, if the pore is very large, what I'm talking about doesn't make sense anymore. So it's like a flat surface. Okay? So the chemistry of the surface also plays an important role. We are not going to deal too much with this because, as Richard already highlighted, from the experimental and computational point of view, this would require more time also to explain and also for you to play with certain tools. So absorption can happen, this is an important point that I put in here, can happen below the critical temperature or above the critical temperature of the gas. So sometimes people say, okay, if we are above the critical temperature, so the absorption does not occur. Because people are, comparing absorption with condensation of the gas. Okay? So condensation, I mean, of course, going from the gas to the liquid phase. And of course, people think if we are above the critical temperature, you cannot form condensate phases. That's true for the liquid gas condensation phenomena, but for absorption this is not true. So you have gases that absorb in solids even at temperatures quite above the critical temperature. And this can be useful from the technological point of view. So I put here just a few examples just to highlight how we can have results of absorption. Yes? So if you look in here, what you have is what we call an absorption isotherm. So isotherm because all these points were taken at a constant temperature, yes? In this case, 25 degrees. And if you look in here, we have methane and CO2, so we are well above the critical temperature here. For methane, it's much higher, okay? And you have here what? Pressure up to 10 bar, so 10 times above the atmospheric pressure. And we have here the absorbed amount in millimoles per gram. So an amount, I will try to highlight this, it's better to express this as an amount of gas. So from the chemical point of view, we should express it in moles or millimoles per gram of solid, per mass of solid. So we have here absorbed amounts as function of pressure. And if you see in here, these materials are absorbing more CO2 than methane. So I will not discuss, of course, the results from the chemical point of view, why some are better than others, just to highlight that you have absorption above the critical pressure, the temperature, and you can use these types of materials to separate methane from CO2. This could be one of the applications, yes? Another, sorry, I need to go.
Yeah, just to, it is the same in the next slide. These acronyms here stand for different kinds of materials, okay?
Yeah.
So different kinds of materials have different capacities, and also the shape of the isotherm is different on going from low to high pressure. And that's why this information is obviously important to analyze the potential of a material for absorption or gas separation application.
So we can afterwards analyze the results. We are not going to do this in this session because it will require more time, and we are going to focus especially on characterization of porosity. But we can, from this raw data, let's call it, calculate selectivity of the separation of carbon dioxide from methane. And you see here that we have several orders of magnitude when we have different composition at the surface. So if we have solids with different, how to say, compositions, we can tune the interaction of the gases with the surface. So you are in the context of a course where probably each one of you are in mind different types of pores and porosity and materials and so on. But just to give this broad spectrum that you can tune the surface of the material to increase selectively the interactions for some of the gases. Another aspect is, for instance, the working capacity. We can regenerate the material, but if we consider that we are going to regenerate only at atmospheric pressure, so if we increase pressure and then go back again and decrease to atmospheric pressure, we have always some amount that stays inside the solid. Yes? And this decreases the working capacity. So if you see in here, the amounts are less than in the initial isotopes that I highlighted over there. So there are some aspects that afterwards can be analyzed to see if the materials are interesting or not for application. Another, I would say, another way of using adsorption is also to characterize the chemistry of the surface. We can use, for instance, water, in this case, these are water isotopes, to see if we have more polar or more hydrophobic materials or more hydrophilic materials or surfaces. Yes? So you see here, for instance, in this case, this very steep isotope here corresponds to where is it? Here, NYI zeolite. So you have cations inside at the surface, and of course, water likes to hydrate these cations. And when we put even very minor amount of water, the adsorbed amounts are increasing like this. Yes? Then, of course, you saturate the material, it doesn't increase anymore. And you have other materials, like for instance, these activated carbons, that from the point of view of surface have the same pore volume, the same more or less size of pores, and the same more or less, how to say, porosity, let's call it from the geometrical perspective, but the chemical nature is completely different. This is essentially carbon. And as you see here, at very low, from very low concentrations of water or pressure up to here to 0.4, so you can even think that this relates to relative humidity, so 0.4 or 40% relative humidity. You don't have any adsorption of water in here. Then it increases like this. So, and then you have other materials that stay in between. Okay, they are not so hydrophilic as zeolites and not so hydrophobic as activated carbons. So we can use molecules also, like probes, to see what is the chemistry of the surface. Well, even for more, how to say, recent materials, in this case I give some examples of MOPs, different ones. For instance, the structure is the same. We are going to talk a little bit about one of these materials, YU66. You are going to see the structure. But we can decorate the pores with different groups, and you see that we also change the hydrophobicity of the surface. Well, the other, just to summarize, to conclude this first part, we can also use the materials in some type of separations in columns, like chromatographic separations, yes? In this case, this was done at the lab, but it can be done at the industrial scale with big columns. In this case, this is a zeolite, and you see, when we inject, this is time, and this is the signal we have at the detector. So, the mixture passes through the column, and then you have first nitrogen that comes out, then ethane, and then ethylene. So you are injecting them at the same time, but they come out at different times. Why? Because in this case, ethylene absorbs much more to the surface of the material, so it takes more time to come out. Yes? But if you change the material, you can have other order of at the output. So inject again everything at the same time, and then you have nitrogen coming out first, then ethylene, and then ethane. So you see, we switch the selectivity of these two hydrocarbons because, of course, the material is equal. I'm not going, of course, try to explain why this happens. This is just to highlight that we can also perform experiments, adsorption experiments in many different ways, also to understand the possible applicability of the materials. So, also from the, imagine that you can perform these experiments at different temperatures, and then you can calculate the selectivity as a function of temperature in here. So we have selectivity here, and temperature here, and in this case, just to highlight that you can do this type of things for different mixtures, like in here, like ethylbenzene, benzene, and hexane, and then toluene benzene, yes, for different types of materials. And of course, this from the point of view of a possible separation application. But what we are going to focus now is essentially in trying to understand, before going to this, how to say, more applied perspective, how can we characterize the porosity of the materials? Because this will always be the first step for using adsorbents, is to understand some basic things about the material, and one of the important things is, like I highlighted at the beginning, it's the porosity. Because these materials are usually such a high porosity that you cannot understand them if you don't characterize the porosity. So, some experimental aspects first is, next time. Okay. So, this is the isotherm that we normally use for characterizing the material. So, this is adsorption isotherm of nitrogen at 77 Kelvin, so it's at temperature of liquid nitrogen. And before performing these experiments, so usually just to have this, how to say, completely clear, we usually call this the adsorption isotherm, and we have in this case here relative pressure, and in here again absorbed amount, and this needs to be at constant temperature. This is why we call it isotherm. So in this case, usually we represent P over P0 instead of pressure like in kilopascal. And why? Because in this case, I'm going from 0 up to 1 P over P0, meaning up to the saturation of nitrogen at 77 K. So I'm going up to atmospheric pressure, if you think about it. So we have the sample inside the liquid nitrogen bath, and we're going to put nitrogen inside the cell and see how it goes. So we have what we call a full or a complete isotherm, because we cannot go beyond this point. Yes? We cannot go beyond the saturation pressure. You put more pressure and then it liquefies. Cannot go. So this is what we call the full isotherm. So the amount, again, should be reported in millimoles or equivalent units of amount. I call this attention that you should try to avoid cubic centimeters STP per gram. I know that most of the softwares that you can perform these experiments in automatic equipment, and most of the softwares will output something like this. You should try to avoid it, in my perspective, and also according to impact recommendations. It's not just me. Why? Because this can mislead you. You can look into this as a volume, and in fact this is not a volume. So cubic centimeter STP standard temperature and pressure, it's an amount. Yes? So the values in here, if they are in STP, can mislead you to think that you have volume like this inside the pores, and you don't have it. Yes? We are going to calculate the volume of the pores in a different way, as we are going to see. So, cleaning the pores, just for you to understand what you need to do. So, the materials usually have impurities inside. So, if it is an adsorbent, everything, moisture, other vapors, and so on, go inside the pores. First thing is try to clean it. How? Using the possible temperature, the highest possible temperature, and the best vacuum you can apply. Okay, to remove everything from the pores. And of course, possible means that we should avoid the decomposition of the solid. Yes? What we want is to remove the molecules that are in the pores without spoiling the surface of the material or even to degrade completely the material. Okay, this is always a compromise between the stability of the material and also the need to remove impurities. In some materials, the impurities that you have sometimes are very hard to remove. For instance, if you are doing synthesis of some hybrid materials in solvents, the solvents may have very high boiling point and sometimes it's difficult to remove. One strategy is try to wash them first with a more, how to say, volatile solvent. Then you have impurities of, how to say, lower, higher boiling point, and this will be easier to remove with temperature. So, after cleaning, you should not put, of course, the material back again in contact with air, otherwise it will completely contaminate the material. So there are two big types of methods. One is the gravimetric method. So as you understand here, you have a balance where we have, how to say, closed balance that is attached to a vacuum system, and where we can introduce some vapor of an organic molecule or a gas. And then we record the weight increase over time, and then when it is stable, we pick up this value as an equilibrium value, and this is a point at your isotope. Of course, you need to have a pressure gauge. Yes, a pressure sensor. So we record amounts absorbed as a function of pressure. Another way is the manometric method, or also called volumetric method. In this case, you have a dosing volume like this. So you need to calibrate first very well this volume, and then we put here a certain pressure, and we open and we give this dose to the adsorbent. The pressure will decrease because you will have absorption here, and then you can use an equation of state to relate the pressure or the pressure difference with the amount absorbed. And then you close again, you give a second dose, and so on and so on. The automatic equipments that you have, most probably, to determine nitrogen absorption isotherms are of this type. One of the problems that I try to highlight here of calculating, let's see. So, for calculating the amounts from these manometric systems, so we need to take the amount in each point x, and then we give another amount, and then the second point is the sum of the first and the second amounts, and the third is the sum of the other big value. So if you put more points, if you ask for, or if you configure the system to ask for more points, you need to remember that the errors are cumulative. Sometimes people think that, okay, let me put many points because I will have very beautiful isotherm, and then this goes giving some, how to say, strange things after some time. It's because you have cumulative error. Yes? And longer experiments also, it's a little bit trickier because, for instance, you have a nitrogen bath, and if the volume of the bath varies over time, then there is a certain calibration that also needs to be performed. So, the measured value is the amount on the mass per sample used. So, C is the amount, and not the specific amount per mass. So we represent amount per gram, but what we are measuring is amount. We need also to weigh the material and put it over there. So to increase, how to say, the sensitivity of the system, we can put more amount over there, if possible. Yes? Because we will have the amount of it will be higher, and then the error will be less. Okay? Sometimes people forget about it and they complain about the reproducibility of measurement. Yes, because if you are putting very small sample, probably the automatic equipment will not complain about it, it will measure it, but each time you are measuring it will give slightly different. And it's not the problem of the equipment, it's because you are putting probably too less amount over there. So the error is big. So longer experiments can also be already talked about. It's problem of void. Yes? So, like I said, the equilibrium needs to be reached. So isotherms are equilibrium points. And how can we know that the system is already at equilibrium? This is a big issue. Yes? If we have stability of mass with time, gravimetric system, then okay, you already know it's already constant. But if you have stability of pressure with time, it can give you some idea, but sometimes it's very tricky because it's still absorbing, but it's not so easy to see. So we need to define some equilibrium criteria, and of course, collect isotherms with different equilibrium criteria to see if they are reproducible. Okay? So let's go into a more, how to say, applied, I hope, more interesting part. So, what can we take out of an isotope? What information? So, we will have access to these slides. We are going to put a PDF with this, so I am not going to too many details about in reading all this, but just to give you an overview. When we take an isotherm of a material, just from looking at the shape, we already know quite a lot of things. One is, for instance, if it is like this, so what means is that most of the absorption occurs at very low pressures. So it means that the absorption potential is very high. It means what? That you have very narrow pores. Yes? So this is typical of microporous materials. Yes? So sometimes the curvature is a little bit more open. What means is, okay, the pores are probably already a little bit larger. Yes? So nevertheless, sometimes we already start to have some narrow mesopores around this value, if it is like this. Yes? And you see in here this, if this is completely reversible, this is physical absorption. Yes? So you can have some desorption points to see if this is reversed. The second type of isotherm that I'm showing here is the type 2 isotherm, and the type 2 isotherm is typical of non-porous or macroporous absorption. And you may say to me, if there is no pores, why do we have absorption? Yes, but you have still surface. If you have fine powders, you have the surface of the particles always, even when you don't have pores. Remember that physical absorption always occurs. And this is usually what you get. So you have something like this, it goes up and then it goes down. Sometimes you have some hysteresis, yes, because you have some condensation in between particles, yes, like this one. Nitrogen starts to condense in between the particles. And another type is the type 3 isotherm, is when we have low interaction between the adsorbent and the surface. Yes? The adsorbate, so in the example I have shown, for instance, for water in activated carbon. The water doesn't like to be at the surface, so it does not adsorb unless you increase the pressure. The type 4 is the isotherm that is normally observed in mesoporous materials. So you have an initial part where you have absorption at the walls, and then you have capillary condensation. So the walls start to narrow, and then you have the formation of a meniscus, and then you have the hysteresis in here. Okay? I will not try to explain in too many details the phenomena of this, but you can think that, okay, it's not reversible. Why? Because the walls start to narrow, and then you have the formation of a meniscus. But the desorption does not proceed like this. It proceeds like emptying, like this. Yes? So you need usually lower pressure to dissolve. Yes? So the type 4 that you see in here, it's the same, but you don't have hysteresis. Usually if you have something like this, it's because the pores are below 4 nanometers. And the type 5 isotherm is something like similar to the type 3, but then you have condensation in between the particles like this. So this is typical of also molecular clustering, and we don't have too many interactions between the gas or the vapor and the surface. And the last one is, how to say, a more rare type of isotherm is when you have layer by layer adsorption, and we have sticks like this. It only happens when you have very, how to say, homogeneous surface without defect and so on, and when you have adsorption of argon and so on in this type of surface. It's not very common. So now we are going to enter in a part where I hope you can, how to say, play with your computers and do some calculations. So how can we do numerical analysis of the data? Yes, this is important. So you have isotherms. Just looking at the shape of the isotherms, you can already know a little bit about your material, but usually we want to have numbers. Yes? So this is the typical thing in science is, okay, let's try to do it in a way that is more reproducible, and I can compare with other materials. And even for my sample, I can compare my samples in a systematic way. Not just by looking at it like, so looking at the X-rays of, oh, you have something. It's, for us, usually at the lab, trying to have a, okay? So we are going to focus for now, on some aspects like calculating the surface area. There are several, how to say, isotherm models. We are going to focus on this one, the Brunauer-Emmett-Teller method. Well, this Teller is the same from the atom bomb. Yes, is the, sometimes people ask, yes, it was the same guy. And they were having a problem with the, how to say, the numerical model, and they went to Teller to help them to solve a numerical series. This is why you have, how to say, this person from this field. Okay, so this BAT method is very used to calculate surface area of material. We are going to try to explain it also for you. And we are going to talk also a little bit about the use of standard isotherm methods. Yes? So to reference isotherms of non-porous solids, or to reference theoretical isotherms. So we can compare our isotherms to other ones to see if we are absorbing more and how much more we are absorbing. So for the BAT method, this is the equation you have. So what I will propose is to go to this address, if possible.
Yeah, unfortunately, we cannot collect the data,
Yes.
the isotherm, so
So
we prepare
a set of isotherms. So as please open your laptops, they are going to start observing. So you have a few, let me
okay, this is sending you to the Google Drive, okay, so the website. Yeah.
So you will go to a Google Drive, and in each folder you have the isotherm, raw data of the isotherm of a different material. Yes. So what I suggest is, if you can, how to say, form a group of 4 to 5 people, it will be easier also to you to work together, and we can also help you on this.
Well, this initial part will make use of Excel.
Yes, in this case it's
Or any other similar software.
what?
Yeah, we can start with the UIN 66, no? No. So your specification. Several folders. Choose the UIN 66. No,
Já está aqui. Vocês estejam sempre a perceber isto. Só azoto e absorção e pressão parcial. Não queria ver a fazer aquela parte da coluna.
Não, eu sou mais de fazer download. So, if you introduce this, you should be able to see the folder.
E aqui basta medir a quantidade de pessoas.
There's an Excel.
Yeah.
Yes. So, everyone is able to access this folder? Not? Okay. We need the link again. I go back. So you see here, in each of these folders, you have a different material. So each folder for a different material. In each folder, you have one Excel spreadsheet with already the raw data of an isotope. And what we are going to do is to play with this raw data to extract the surface area using the PET method, and afterwards also the micropore column.
The important folders with materials are these, okay? So UIO, MORE, MIL, and DTS. Okay, then there are some different.
So, for instance, if you enter in here,
Yeah, but put again the link because some people could not access yet.
Teşekkürler. Yok sağ ol, sağ ol. Ne kadar bekleyeceğim?
Buyurun hocam.
Kaç dakika bekleyeceğim?
Hocam 10-15 dakikasında
Já está a condição.
It is a Mac issue, okay, so it will not work now. But if you go to this site, I think if you access typing URL, then you can add just the code. We will send the link using the chat. Yeah, but if you connect to Zoom, are you or not? Okay, at least for the people that is attending from abroad.
so I just have sent this in the chat. Yeah, but for people that are not connected to the knowledge, it's more complicated. But in principle,
Manda só o e-mail.
já.
Yeah, it is working now. For some reason, Mark is against this tiny warehouse.
Mac doesn't like it. Okay, are you able to at least see, have the screen in front of you and open the Excel spreadsheet? So you can choose one material, and what you have, essentially, it's a column of P over P0. I will open here one example, okay? I will open here one example, but you can open another example, what you want, because the calculations will be the same. Yes? So let's see. So let's see, for instance, if you open
There is some delay.
yes, between this and
Yeah. Okay, but this is UIO 66.
I just opened here this example. So why? There is some delay between the two, okay? So the first column, the A column, it's P over P0. So it's what? It's the relative pressure. So it's the pressure that is measured by the gauge divided by the atmospheric pressure. And the P0 can be eventually taken experimentally, or it can be assumed as a constant. Yes? Because there are some systems where you can also measure the P0. How? Well, you put a certain amount of gas, a little bit above the atmospheric pressure, then you put back liquid nitrogen, and then it will condense inside the tube, and then you measure the pressure you get. So this is the P0. You cannot go beyond this pressure. Yes? So this second column, so the B column, is like I told you, most of the times you have the systems giving you cubic centimeters in STP per gram. So this is the equivalent volume at standard pressure and temperature. Why the systems are still reporting things like this, I don't know. Many times I already told people from the companies you should not, okay, but they are still doing this. I would say that it is for historical reasons, because some of the systems you just compress a certain volume of gas at STP, and then this gas was absorbed, and then you just report, oh, this amount of volume, but it doesn't make sense, okay? We should, if you are reporting an amount, you should use the units of mole or millimole, okay? So, what you need to do is to transform this B column into amounts of moles or millimoles per gram. And you have here the conversion here. So, if you see in here, this is the conversion factor. So you just multiply this column by this value and you will get millimoles per gram. This is just a conversion. Okay? Yes? Simple thing. So now we have.
This is the same way for materials?
Yes, this is just a conversion factor. This is just to convert cubic meters STP,
For N2.
for N2, yes.
Gas is always the same.
Actually, this conversion is true for any gas. If you just use your how to say, the ideal gas equation and you calculate 1 cubic centimeter at standard pressure and temperature, and you calculate what is the N out of it, you will get a conversion factor like this. So you just multiply this column by this, and you get the amount. This is what you should get. Yeah? Okay? So now you have the A and the C column, with the data to apply your BAT equation. Yes?
Can I put a question?
Of course.
This data was obtained from a commercial device.
Yes, probably.
What is the surface, nature, and what is the gauge?
Yeah.
Just numbers, sorry. Too much numbers after all.
what is the nature, what is the material.
Yeah, what
Yeah.
Yeah.
We will see the material afterwards. It's a UIO 66, I will show you. You are. So let me see if I can show you to you here. Okay?
Okay, for those using Windows,
So let me see. So it's not necessary to perform the calculations, because you can perform the calculations of the BAT surface area in any type of material, as long as you have what? The isotope. So I'm showing the material now because your colleague is asking, but you don't need it. Actually, you can just go outside, pick up a sample of a powder, material, whatever thing, and you can measure the surface
You put
area.
inside the machine, and you put that sample inside the machine, and you get this data.
Yes. For instance, some years ago, I was having a project where people wanted to see the surface area of ancient mortars that were used in ancient churches and so on. So you pick up a sample of the mortar from the wall and then you can measure it. The problem is, if the surface area is very low, you need to remember that what you are measuring is absolute amount. You are not measuring per gram. So if the surface area is like 1, 2, 3 square meters, you don't put 50 milligrams of sample. You put 1 gram or 2 grams of sample. Yes? So you are multiplying. Yes? This is just an experimental aspect.
that is that we must perform the experiments with all the care that was already explained. So we must dissolve all the contaminants and so on, and only after do the experimental.
So
So the structure is of a metal organic framework. Okay, so in these green polygons you have the inorganic nodes, and then some organic linkers that are connecting these metal organic, these inorganic nodes. Okay, so this is a model.
So you have voids. You can choose another folder and see the other zip files of other materials. There are titanium silicates and there are also zeolite. Okay?
We will show it in.
Afterwards, we
will go to that
go
part.
to this just to show what is the material. So let's go for the calculations. Where is the Excel spreadsheet? So in here, so you have the data, amount, and P over P0. What you need to do now? You need to apply the equation. Yes? So let's go for the equation. So what you need to do now is to do this calculation. So let me.
So basically,
Okay.
you have already this, okay? That is your X.
So
But you must calculate this part here. Okay?
So what you need to see in here, so how can I apply this equation to my data? I have P over P0 and I have N, the amount dissolved. So if you look into this, this is a strange equation. No, it's not so strange if you look that this is your Y, and this is your X. Yes? And then this
Slope
is the slope and intercept. Yes? So you can make a linear regression of what? Of this against this. Oh.
It's working, yeah.
No. I'm right.
So can we change the color because the black is not maybe? Yeah. Yeah, right.
So what I suggest is go for the Excel spreadsheet, and what you need to do is in the next column, yes, afterwards, you calculate this. So you divide P over P0, that's the column, and then you divide over N times 1 minus P over P0. And then you can,
Remember that you have already this, so.
yes,
This is in the A column.
this is already there. So let's go back again to the, sorry.
Listen for a moment, claro.
You have to click on the X on the upper top of the screen. No, in the upper top, see, finish it there.
So, you see, you pick up this, then this value, and then you calculate P over P0. So this over this times 1 minus this. Okay? So this is A over the C 1 minus A. Yes?
N.
Okay?
Aqui no.
Não estava no momento já. So you should have something like this.
So, AC, you should roll that.
You should write something like this, okay? Yes?
Yeah, this is it. For the first step.
Okay?
A6 divided by C6 times 1 minus A6.
Everyone got it? Yes? Can I move on? So what you can do afterwards is
We feel like the way the man.
we calculate this, and then we can plot this is your y, this is your x, and you can do what we call the PET plot, okay? So the PET plot is essentially so it's essentially this. So your colleague already noted, yes, but this is not a straight line. Yes, this is the second problem we have. Okay, the first is to calculate. The second one is to remember that usually this should be applied in between a range. This model is only valid in a range of P over P0. So we can calculate for everything as a first approach, but then we should narrow down our analysis here. So let's try to do it. And for instance, we can. So we now usually 0.05 adds to 0.1 or 0.5, something like this. Yes? Let's try to put one more point. like this, and even one below. Okay. Then you can add a trend line.
This is the same graph as before, but now only this.
Only for this knuckle part. Yes? Okay?
Everyone is following this, okay? This graph this is X, this is Y as before, but only
Yeah?
specific and
One important remark. This model was developed for non-porous surface, and now you may, of course, ask me, why are we using this for a porous solid? Yes, we need to remember that this model is based on stacking molecules in a planar surface. So we need to think that this is not giving you, how to say, the real surface of the material, but it will give you an apparent surface area. So this material absorbs the same way as a certain flat surface area of the size you are going to calculate. Yes? So this is especially important if you are going to try to do very special calculations with this value as a real surface. Yes? Because material is porous. Where is the surface? It's not a flat surface. It's very yes, this is what I'm going to talk. So this model, because this model was developed for non-porous surface, we need to narrow down at this section.
No, it would be important to listen to what you are going to say, because it is important to understand
Yes.
why this selection is
Why this is important? Because this model is for non-porous surface, so it needs to be before condensation in the pores, otherwise it doesn't make sense anymore. Yes? So usually this section in here, as you see, it will give a straight line, and afterwards it will increase like this, because it's not applicable anymore, it's condensing already in the pores. Yeah? So usually this range is the range where we can apply this equation and get a value that will give you an equivalent surface area of a non-porous surface. Yes? Okay? So what you need to do now is to note these values and proceed with the calculations. Proceed how? Let's go again for the presentation. So if you look in here, if you look in here, you have slope and interception from here, and if you put 1 over slope plus interception, as you have in here, you can calculate the NM. The NM is the amount at the monolayer. So your monolayer of adsorbed molecules can be calculated with this.
And now you can understand why we are applying just in that range.
Because then you need to, it's
You
where you
just-
have monolayer.
In principle, you have
If
just
monolayer, if it already starts to condense in the middle of the pores, then it's not applied.
Otherwise, this is
Doesn't make sense.
valid. Yeah.
The C is the energy, or I would say, the interaction energy with the surface, and usually it needs, well, one way of looking at is to see, not to extract a real value, but at least to confirm if this C is positive. Usually the C value, when you are fitting, needs to be positive. If it is not, then you should consider changing a little bit range. And how can you, afterwards, calculate the surface area? So, if this is the monolayer, then, let me go for the next slide, then the monolayer can be calculated like this. So, if this is a monolayer of molecules, if I multiply by the Avogadro number and by what? By the area of each molecule at the monolayer, which is this value here, sorry, in square meters of course, this units here. If you pick up your monolayer value and you multiply, you should obtain your surface area. Okay? Can you try to do it? Yeah? So, first thing is, let's go back. First thing is, calculate the monolayer value. Yeah? 1 over S plus Y. So, slope intercept of your line. Yeah? Okay? And then, everyone knows the Avogadro number? Yes? Do you remember? Não, say 6.023. Yes, 10 up to 23. Yes? I didn't put over there because I thought it should. Okay. Levantaram? Conseguiram? Okay.
Look, left we are assuming something like this.
Yeah?
So our probe molecule is
This.
this is a spherical shape.
Yes? So, usually the software. So usually the softwares are. O ganho normalmente é sempre a rua 0,0 e até 0,0. Mas em princípio também não devia dar uma diferença, porque eu continuo com o resto, ou seja, o mesmo posso não vai ver.
Pois é, e também os números corporativos.
Isto no nosso caso
Até que vai em exceptions.
aqui, 0, so 0.1.
Okay, for the wheel 66, slope is this number here, and the intersection is this number.
Yeah, but you can do it for the other example.
It is here, okay, we use the function intercept just to add a few more digits, okay, so 8.491 times to the 10 to the minus 4.
Yes. So,
and here these numbers again, okay, so slope and intersection.
So, and have you been able to calculate the value? Yes? So, can you someone? The surface area.
46,000.
What units? So, what evaluation? 800 e tal metros quadrados. Não sei qual seja So you need to remember one thing. You need to remember one thing. The units are in millimole. So
You have to put it in more.
10 times less, 1000 times, yes. So remember, if you are using Avogadro's number, it's one. What are the units of Avogadro's number? Oh, 1/mole. Yes, mole minus 1. But our units are in millimoles. Yes. So if it is in millimoles, is 1000 times. Yes. Yes, exactly. So around 800 square meters. Yes? Yes, okay? Okay. Make sense? Huh?
And then it's
8.68.
8.68. So this is and then it's just replacing adding the government, the volume of the probe, and dividing by 1000 in order to have millimoles. So the units are millimoles.
Okay. And I move for the next example. So
everybody could reach at least a number like this, or?
Yeah. So one important thing is to remember that this value, you have an error out of the fitting of the curve, and of course this is the statistical error, but or the fitting, but you have another error which is the error of the measurement. Yes? And if you have like 800 square meters per gram, if you are comparing with another batch that you see that make the synthesis and then you measure it again on another batch and you find out that okay, there is 20, how to say, 110 and 20. Really, what means is that you have essentially the same material, yes, from this point of view. You don't have sufficient accuracy to distinguish these small details, yes? Okay? So, the other example that I'm going to put forward, let me move because we need also to pass to more, how to say, theoretical calculations. So, just some pitfalls in here. So the model, as I already highlighted, assumes a non-porous surface. Thus, the values we have for microporous material don't have a real physical meaning. Yes? It does mean that you have 800 square meters of surface plus surface. It's a porous thing. Yes? This is why there are other methods that we are going to talk about to calculate the microporous model. So the model also assumes a homogeneous adsorption energy at the surface, and this is not true for the large material, majority of real materials. You have parts of the material, for instance, in this case, which are benzene rings, other parts which are zirconium oxide clusters. It's very difficult to conceive that the nitrogen molecule will interact with the same energy everywhere. So please take also this into consideration when applying this. Nevertheless, this is a useful model to compare your materials with others, of course. But you need to remember some of these pitfalls. So the range of P0 for the VNT equation should be the same for comparing values among the different samples. As you have seen, if you put one or less value, the value also changes. So if you have a batch of samples and you want to compare these samples, at least you should try to use the same range of P over P0. Yes? Otherwise, you have some differences that are because of the different ranges selected. Okay? And as you have seen here, if you want to measure surface area of the material, you don't even need to measure the full isotope. You can eventually just measure on this range. Yes? So let's move. So there are other equations like, for instance, the Dubini equation, where you can, how to say, apply this type of equations more or less the similar way that we have done for the DT equation. This is a different equation. In this case, you can extract what? The adsorbed volume. Yes? You can transform the amount to liquid-like volume, like we are going to do opposite, and you can apply this equation. We are not going to do this example. We are going to jump to other types of strategy, which are the comparison plots. So we have the T-plot method and the alpha S method. They rely on comparing the isotope that we have measured in the actual sample with some standard isotopes. Either taking from, what to say, more theoretical isotopes or even from other real isotopes of non-porous solids. So the chemical nature, so the standard isotope is in a non-porous reference material. Yes. So a material where you don't have pores. So we are going to compare your material, which has pores, with a material that doesn't have pores. So the chemical nature of the material, reference, and your material that you want to study should be the same. But this is quite often very difficult. Nevertheless, you can say, okay, I use this standard isotope. It can give you indication of the micropore volume, the external surface area, and also the surface area of the sample. And we are going to use also these values to compare with values that we are going to obtain from other approaches using the crystal structure. So often we assume the density of the doped phase. You need to assume it, and usually you assume that the liquid nitrogen the density of the liquid nitrogen is the same density as your adsorbed phase. So we assume that the nitrogen is condensing with the same density, which is something that you are really not sure. Okay? So you need to be very careful with these assumptions. So it's very useful to compare different samples. This method is very useful for comparing samples. And how can we use? Let's see if we, okay. So the strategy here is a little bit different. What we need to have is, instead of adsorbed amount, we can transform this into adsorbed volume. Yes, so if we know the smaller volume of the liquid nitrogen, we can multiply the adsorbed amount by this value and obtain volume of adsorbed, yes, nitrogen. So we can plot this volume, yes, and in here we plot the thickness of the monolayer, of the layer that is adsorbed. And if you see it in here, in the T-plot method, we are assuming that the adsorbed, so what we put in here is essentially the adsorbed amount over the adsorbed amount in a monolayer times the sigma, yes, of the molecule. So in this case, the area that we have in here. The section that we have. So there are many, how to say, proposed equations. One of the most used ones is this. Relates this thickness with P over P0. So actually from the, how to say, more pragmatic point of view, you take your column where you have P over P0, you transform this column into thickness. Yes? Then you have your X and your volume in here. Then you do the plot. You should obtain something like this. And if you remember, so 0.4 is around, more or less around the thickness of the monolayer. So you see it in here, 0.4 in terms of nanometers, so 0.54 in terms of angstrom here. Okay? So what you should try to do is to see that in this range, more or less, you should obtain a line where you fit your line, and then you extrapolate in here to see where is the intersection. So if this is the thickness of the monolayer, it means that, so we are comparing with a non-porous surface. Yes? If this was a non-porous solid, you would have something like this. Yes, because when you extrapolate to zero, so you have more or less surface in your material comparing with a non-porous surface. But you don't have micropores. So you could have a material that absorbs more or less, but when the thickness is extrapolated to zero, it should give the same value of zero. Yes? So since it does not give the same value, so this value is the value of the micropores. You see, this excess that you have in here of your material comparing with the non-porous material is the volume of the micropores. So from the pragmatic point of view again, you fit your line, you just extrapolate here, and you see what is the value you have in here in volume. So this is your microporous volume. Immediately, yeah? So let's try to do it also in the Excel spreadsheet. Yes? You need to calculate this. Yeah?
It's not the same, right? Is it the same?
You can use whatever spreadsheet you want from the example.
Yeah, you can use
You can use the same if you want.
And basically, what you must calculate is this T, you use the numbers, and then for the first cell, it should be a T.
Yes.
Because it's P above P0.
So I will go very quickly here again. So you see, let me delete this. I understand. Yes. So again, so let's see, from the pragmatic point of view, what to do? We have P over P0, yes? So we just apply this equation. So 13.99 and we divide over
What is the equation? This should be log, okay?
Yes.
Not use the line. Explica só por cada forma. E agora eu vou ao ritmo.
Okay? It should be something like this. So you already have a column with your thickness. Yes?
Sorry, it is not clear, but it should be there, okay? So it is the square root
So the other thing, yes, so to the square root, you have 0.5, yeah? So in here you have thickness. Now you need to multiply this by the molar volume of liquid nitrogen in millimoles again, don't forget your units, yes? In this case it's cubic centimeter per millimole. So if we multiply this amount by this value, we get a column of adsorbed volume as liquid nitrogen, yes? So we just, how to say, go in here, multiply by this, and then you should give, yeah? So you see, the first point is 0.3 cubic centimeters, 0.1 and so on, okay, per gram. And what you need to do afterwards is, okay, we plot this. And you have the type of graph that I just have shown over there. Yeah? So what you need to do is to choose here some points around 0.4, between slightly below 0.4 and slightly above 0.4, and why 0.4? Because this is the size of your chromolyc nitrogen, yeah? We are calculating for a monolayer. So if it is already well above, then it's not a monolayer of thickness. It's not a thickness corresponding to a monolayer. Yeah? So if we use a value around here, let's see. Okay. So if we just choose, for instance, these points in here, yes, that we have with the different solver, yes, and then we fit this and see what is the interception. You already see that it should be close to 0.35. Okay? So we can choose this and a trend line. And okay. So you see, everyone followed what I was saying? Yes? Okay? If so, this value we can use, for instance, for comparison with other methods that are based on the structure of the material. Yes? So, Richard is going to start talking about using the structure of the material obtained by different methods, how to calculate some type of parameters, including porosity and pore volume. And okay, this value can be compared with theoretical values, let's call it, okay? And everyone, it's okay with this? Any questions, doubts? No? So, most of the softwares already do all the, how to say, automatic machines already do these things. But I advise you to try to understand a little bit and try to do this by yourselves, because quite often these softwares are not, how to say, looking if you have a straight line in here. Sometimes you don't have it and it just nevertheless it gives you a strange value and then you don't understand why. Yes? Same for the VAT equation. Sometimes you can go for the software and try to tweak a little bit and so on. But this is also to highlight that, okay, and you need to understand a little bit how the method works. From this, we are not going to do it, but from the slope, we can also calculate the external surface area. Okay, I am not going to do it, but if you want to see it, you can also see it in the literature that I am going to give in one slide. It's not very difficult, nevertheless, we have to pass to another, yes, set of time, okay? So, let me jump again to the slides and just complete very quickly this part. So, with this method, we can, with this method, we can calculate the micropore volume. We could also, from the slope, calculate the surface area, external surface area, yes? Usually, if you have a very microporous material, the external surface area, it's very small comparing with the value of the area obtained from the VAT equation. Yes? And just to highlight here that there are other methods where you can compare instead of a standard picture, you can compare, for instance, in this case, with a non-porous silica, and in this case we are analyzing this porous silica, which is a mesoporous silica. What we are expecting, okay, if this is a mesoporous silica, then it should give 0 volume of micropores. And if you use the proper reference isotope, you see, okay, close to 0, or very close to 0. Okay? The values you have in here corresponds to what? It's already above the thickness of the monolayer, it corresponds to condensation on the mesopores. Okay? So we can also calculate pore size distributions. We are not, of course, going to do this in here, but just to remember that micropores are below 0.2, mesopores we call them when they are between 2 and 50, and macropores when they are above 50 nanometers. Yes? Sometimes people talk about mesopores without understanding that all of these pores are actually on the nanoscale. Yes. And we can also say plot the pore size as a function of volume. How can we do this? We can use different methods. I'm just going to show very briefly some of them. So one method is like this. You can, for instance, from the P over P0, calculate with this, how to say, big equation. But you have values for all these variables for nitrogen, and you can transform what? Your PP0 column in what? In L. Yes? So in size of the pores. Yes? Okay? And well, actually this is starting already to resemble with the part that the patient is going to talk about. One critical point is we need to assume a certain geometry for the pore size distribution. Yes? We need to assume the pores are cylindrical or the pores are split shaped. This is a pre-assumption. Yes? And it changes the pore size distribution. Another strategy are the ones based on what we call the local isotherm or the integral isotherm. So the isotherm we are measuring is, how to say, the integral from the local isotherm with a function of the distribution. Yes? This is, how to say, a hill-posed problem, because to solve this, this is what we have and this is what we want. Yes? This is, I'm not going to talk much about mathematics, but from the mathematical point of view, this is not solvable very easily. There are some, how to say, this is the inverse Laplace transform that we need to use in here. But what usually we use is some local isotherms, yes, some kernel of isotherms, and these can be obtained by DFT, by GCMC or whatever, and then we see what is, how to say, the mixing of these local isotherms that give the isotherm you are measuring. Okay? Of course that we need to assume also a certain chemistry and also a certain shape of the pores. Yes? So, one of the most used ones is the DFT method. DFT method not in the sense that, for instance, Richard is using. This is a numerical DFT. So this is a density functional theory, but functional of what? Of the density, but the density of molecules inside the surface, not the electron density. Yes? But nevertheless, it will give what? A certain kernel of isotherms, and then we can calculate the pore size distributions. Yes? So actually, actually these methods can, how to say, help you to analyze the pore sizes from very narrow pores up to very, how to say, wide pores. These methods are good because they are not just to be applied to, how to say, the initial part of the isotherm, but for the full isotherm, yes? Because you are comparing your isotherm against a set of kernel of isotherms, yes? If you have, how to say, these theoretical isotherms on the mesopores part, you can also extend this, okay? I give you here a set of books and texts that you can read, and then I'm going to pass to Richard that is going to talk about the.
Okay, basically, from the computational point of view, we rely not only on the experimental information, okay? we rely not only on the experimental information, the social data, but we also rely on very valuable information that comes from those scientists that collect the structures of molecules and materials. Okay. Before you were interested in knowing how to display the structure of a material. We have in different folders some files that can be opened with this software that is named Vesta. Okay. Why this software? Just because it is free and it is very easy to install. At least in Windows, we have it in the Google Drive folder. Search for Vesta, and there is an executable inside, also named Vesta. Please double click the executable in order to start this tool. Basically, structures of materials and molecules or very small compounds up to macromolecules, okay, they are stored in very large databases, okay. There are many databases, I will show some in the next slide. But mostly for inorganic and small organic compounds, the databases work with a file extension that is named CIF. We will see what this means, okay? The extension is CIF. There are some other extensions that can be appear. And in the case of macromolecules, so big structures, proteins, or enzymes, or similar molecules, there is a database that is called the protein database, and they use this kind of extension that is PDV and stands for protein database. Okay, there are some databases that are collected here, but there are many more. Okay, these two databases in the top, they collect essentially then when you go home or when you have the slides, you can click and this will send you to the database, okay, that is stored somewhere in the internet, okay. But these two here, they use essentially CIF file format. The first one collects mostly small organic and small organic inorganic systems. This one is quite clear. It is a database with structures of minerals, okay, crystal structures, the protein database, and there are some other databases that are becoming very important because they collect several. And first in this case, I guess that the current number is 250,000. 250,000 compounds that you can find in the catalogs, like I don't know, one catalog of chemical compounds, where you buy stuff to Sigma Aldrich, of course, Sigma Aldrich and other kinds of companies that sell small organic compounds that you can then use to make larger molecules. And these kinds of databases are becoming very important because they can be used to, for instance, to develop new drugs. So they are very interesting to perform what is known as virtual screening. Okay, so you have a library of these compounds, you have a target, you make a virtual screening, you check the ones that bind more or less to the target, and you can select those compounds for future development projects. But essentially here we are more interested in databases like this, okay? With the structure of minerals, or in this case like the zeolites or metal organic fragments. The structures can be obtained experimentally by different methodologies, okay? For instance, in gas phase, a very useful technique is microwave spectroscopy in the solid state, neutron and X-ray diffraction. For instance, for big macromolecules, enzymes and proteins, nuclear magnetic resonance in solid state is also very useful, and in solution also the nuclear magnetic resonance. Computational methods can be used to obtain very accurate or very well-defined structures for small compounds, but when we go to larger systems, the calculations become more complicated because they are very time consuming and structures cannot be obtained with the same degree of volume. But what is this CIF file? Okay, the information, this CIF stands for crystallographic information file. It was introduced several years ago. Okay, it can be easily readable with a text editor. We will see how to do it, and also can be used with a software like Vesta to display the structure of atoms. Okay, it was adopted by this International Union of Crystallography, and it is being maintained. There is some thoughts to develop what should be named a CIF2 file, so an improved format for storing crystallographic information. So this will be the first exercise in this hands-on session. So if you go to the same folder that you were using in the previous exercises with the isotherm, you can use your favorite text editor, okay, Notepad, WordPad, whatever, to open one of these CIF files that are there, okay? Lucas, can you help me with this? Because I use another text editor in my computer. If you go to there for a moment, if you go for instance to the UIO folder, as you can see, you have the Excel file as before, and you have also the CIF file, okay? So you can open this, because this is a human readable file, so you can easily display it. And basically, this is how it looks like, okay? There is a lot of information inside. We'll see in a moment how we can use this. But very important here are these lines with the length of the cell, okay? So each material, if it is crystalline, we can display it like a collection of boxes that here are simplified as cubic boxes with atoms that are here. So the structure is replicated in 3 dimensions, okay? And the atoms are located inside. That's why we could display before the structure of the YO66. Then there are several relations, symmetric relations, in order to multiply the atoms to obtain the final material, but I will skip this. Let's go down just to, and at the end, this ends with the kinds of atoms that, or the nature of the atoms in our material. So zirconium, we have 2 different types of oxygen atoms, they are not equivalent, and 3 carbon atoms. As you are probably suspecting right now, these materials look a little bit strange, because this is a moth, this is built with metal oxide inorganic nodes, but there were some organic ligands. As you can see, hydrogen atoms are missing. And the fact is that, from an experimental point of view, when you perform for instance, X-ray diffraction, since these atoms are very small, it is very difficult to locate them. Okay, you cannot locate the positions of these atoms. And what is done is to use chemical intuition, and because the people that synthesize the materials, they know more or less what they included, then they place automatically the hydrogen atoms. So the idea now is to use Vesta, okay, to visualize the structure. So you double click this tool, and then you open the zip file. Let me
So can you open sorry, I will close this.
If you are using Apple, it will not work. It should work with Windows, because
If you
can
double
download it.
you should download the works in Mac, but not this version.
You can download it. You can just download it.
Yes, if you go to the web, you can download the Mac version.
the executable that is in the folder.
It's not for Mac.
In the Google Drive is for Windows, okay?
Of course, you can go and pick up the version for your computer. Yeah? So if you open the file, if you open Vesta, one way of opening the structure is, for instance, if you just go
Probably many of you already used this before, okay?
so if you just
Drag and drop.
if you just drag this on top of Vesta, it will open the file. So for instance, you can open it, so this is one structure. If you go for another one, it's the same thing. For instance, as LI, you just open this, and you can open as LI, and so on. So,
Okay.
okay, this is how to say, this is the modernized LI.
This is an interesting example, but because as you can see here, there are some oxygen atoms, red stands for oxygen, that are lost in the middle of that channel. In fact, these are some of those solvent molecules or molecules that were absorbed from the atmosphere, okay, before they perform the determination of the structure. As in the experimental determination of the absorption isotherm, if we are interested in analyzing the internal structure of this material, we should a priori remove these atoms, because when you use vacuum, you are supposed to remove these molecules. Okay? They can be either water, they can be other solvent molecules that were left. In some cases, what happens in the experimental samples is that parts of the structure are not so crystalline as the ones that we have here, and sometimes the difference between the calculated information and the experimental information is attributed to those defects. Okay, can we move on? So, the information in this, as you can see, is stored in the zip file. Contains the length, the angles, the volume, okay, of the cell. Some other important information for the crystallographers, like the shape of the cell, that is also important for the code like Vesta to display the structure. We didn't it before, but we can extend the structure that we see initially in the screen to have more cells, okay? Instead of showing just a unit cell, we can extend and show more cells. Okay, and basically we have the atoms as I saw before, and there is more information including the authors and citation. So it is a very useful file, because if you don't know from opening this file, but if you dig a little bit, you can understand who performed the determination, and you can have also the citation to the work. Okay? We will use a code here that uses a slightly different format to display in the structure of the material. This is the XYZ file, okay, and as you can see, it is limited to a very limited information. Just a line with the total number of the atoms, then a comment or a blank line, and then n lines with the atoms that are included in the structure, okay? Basically, for the case of the water molecule, XYZ file is reduced to something like this, okay? We have the total number of atoms in the system, a comment, and then the positions of atoms in space. So the next step with this exercise is to export the structure of the material in this XYZ format. And to do so, you go to Vesta and you select the option Export Area. Choose the YO66, okay, and better. Export data. Okay.
And then you should have checking here if it is a XY.
Yeah, choose the option XYZ
Okay.
format.
So as you probably now are wondering, when you export like this, you lose information. Yes, from the sys file to the XYZ, you have less information.
Yeah. So select no in this second.
Yeah.
So basically what we are doing now, instead of having a few atoms that we use several symmetric operations to obtain all the positions, now we are writing in a single file all the positions in space that are inside this cell volume, okay? So we will end with a file with, if I remember well, with 840 something lines. Can we display this? So 884 positions, okay, so many positions corresponding to zirconium atoms.
So you see here,
Okay,
then you have a list.
oxygen, all the positions, and whatever, and the file will end with the, I guess, with carbon. Okay. And in the In the following, we will use what is named as Lennard-Jones potential. Okay, it is this equation here that was proposed almost 100 years ago by this Sir John Edward Lennard-Jones to describe, and please note, to describe the interaction between molecules like, in fact, in the first article published by this person, to describe the interaction between argon atoms. Okay, so spherical species, okay, that interact with each other very weakly. Okay, as Moises was saying in the beginning of his talk, interactions that include mostly this kind of interactions, dipole-dipole, dipole-induced dipole, and London interactions. So, characteristic of systems that are interacting physically, okay, without the establishment of chemical bonds, or at least electron transfer from one orbital to another orbital and back donation, as it happens in case of consortium. And basically this gives us the potential energy for these spheres that, when they are at more or less large distance, they feel this attraction, okay, until a certain point that starts to become unstable, this interaction, because we are compacting the spheres and the electron clouds are overlapping. So in this equation, R stands for this distance between the particles. Okay, sigma is the distance at which the intermolecular potential between these particles is zero. So at the line, the Lennard-Jones potential crosses energy zero, and epsilon basically is the depth of this well. Okay, there is a Excel file in Drive, Google Drive, that is called LJ potential or something like that, that you can use to play with this. Okay, so you can use different sigma values, different epsilon values, and see how this how the shape of this curve changes. But what will be important to see is that, sorry, before going to this, so this was used to describe the interaction between the same kind of atoms. Okay, but what happens when we consider different atoms? Basically, the Lennard-Jones parameters are obtained for properties of single atoms. In order to avoid a huge amount of parameters, there are, or we often use what is named the combination rules in order to obtain sigma parameters for different pairs of atoms. If this is atom J and I, and this is atom J, sigma parameters are obtained like this, so arithmetic average, and epsilon parameters are usually obtained as geometric average. So the idea is to open the Excel file and confirm that the well test is found always for this when the R, so the distance between particles, is exactly 1.122 times sigma. Let me see if I can find the file. So it is named LJ potential, and you can display and play with it. is already there, okay? So this is the Lennard-Jones potential for epsilon equal to 0.5 and sigma equal to 0.3. If you change these values to something else, for instance 0.7, you will see that now what happens is that the well depth is now larger or deeper than before, just so you can have an idea. But basically, if you replace sigma for different values, you will see that the minimum is always found when R is equal to 1.122 times C. Okay? So you will be able to see that. Please PowerPoint. So now we will use a tool that was developed by Professor Wes Sarkison, a friend of us, okay, he works at the University of Manchester. The code can be obtained from that GitHub server, okay, but we already download the Windows version that is also stored in the Google Drive in a folder named Laser or something. Okay? And basically, what this code does, okay, now we are using all the information that came from the experimental side. Most of it was already summarized by Moisés, okay? And if we have a cell, so that's why I was introducing this concept of the crystallographic structure, so we must have the knowledge about the positions of the atoms in the adsorbent, okay? If we are considering a solid adsorbent, we must know how are they located in the volume, okay? What this code does is to divide the entire volume in very small cubes. The naming introduced by lab is cubelets, okay? So they divide the cell in these cubelets. This is important, probably you will know right now, but basically then we will use an algorithm, okay? In this code, they use the Monte Carlo algorithm, could be any other kind of algorithm. The idea was just to add spheres inside of the volume of the cell, and when they were overlapping, those positions are not considered. If the positions are not overlapping, they are considered. And basically, why this information about the cubelets is important. So this is the probe. It can be, for instance, like in the experimental work, nitrogen molecule, okay? A sphere that represents the nitrogen molecule, but it can be helium or a point, it can be something else, okay? And here we have the atoms of our adsorbent, and basically we compute these, where these interactions are possible, okay? That by these Lennard-Jones potential, they are not appearing in the energies that are positive, okay, because the molecules will be overlapping. And this information is quite important, because if we can follow a path in between the atoms of the adsorbents where the cubelets are connected, we can say that this channel, the molecules can diffuse or can move freely through the channel. Well, in this case, where these cubelets are not touching, this flow of molecules is not possible. I don't know if I touch something, it is working. And basically, the calculation works like this, okay? So if the atoms are overlapping, like in the case of these red dots, structures are disregarded, okay? Otherwise, they are considered. Okay, depending on the radius of the probe, we can reach narrower channels than when the probe is big. The problem of the Monte Carlo algorithm is that if we did not consider this cubelet approach, basically the Monte Carlo does is puts randomly the probe molecule inside the volume, okay? And if the interaction energy is correct, okay, there is no overlapping of the atom, things like this could happen, okay? So this is a pore that is surrounded by the material and is not accessible to the gas and could be considered a pore, or things like this where big pores are connected to a channel by a very narrow channel could be also accessible, okay? But using the approach of the cublet, okay, we know that we could not go from this to this side, okay? And now I don't know how to. I destroyed everything. Paula, can you help us with this? Okay, maybe. What? It is working. Okay.
Not work with computers.
This is not a computer, this is a screen, okay? So,
Technology.
these are the cases where these are accessible, for instance, to a very tiny probe. In this case, it is not accessible to a bigger probe. This is the definition of the pore limiting diameter that more or less Moises talked about before, largest cavity diameter, the definition. So, to end this part, okay, some more important information. Basically, we can compute or have an idea what is the geometric volume. Basically, it is the volume that is not occupied by atoms of the solvent, okay? And this surface that surrounds the area of these atoms that are oriented towards channels is usually named as the van der Waals surface, okay? There are two additional definitions that are important. One is this probe center accessible molecule, and basically we compute this by rolling our probe following the surface, okay, but we consider just this center, so the surface is defined by the center of the probe as it rolls over the atoms of the absorbent. The probe occupiable volume is computed in similar way, but in this case, the point of interest is the nearest point of the probe that is contacting the atoms of the adsorbate. And basically from this to this, as you can see, there are these regions where the sphere cannot reach. That is the difference between the geometric volume and the probe occupiable volume. So the Lennard-Jones is a crude approximation, okay, because we introduced before, it was developed for rare gases, so it should work for rare gases that are interacting with each other, but they also work for the interaction of rare gases with adsorbates because the interactions are also physical interactions, homonuclear molecules, or molecules without polar bonds like methane. For instance, in the case of carbon dioxide, where you have polar bonds, and in principle, oxygens will be partially negatively charged and carbon will be partially positively charged. It will be important for a correct calculation of this potential energy, the calculation of the Coulomb potential. Basically, it is the product of the charges in atom I and atom J divided by the distance between these particles. Problems that may appear, okay, the structure of the adsorbent is considered rigid, okay, it is okay for many solid materials, but in some others, they change, their structure may change with pressure. There are possibly, you already know, metal organic frameworks that suffer from what is called the breathing effect, so the structure. We have one example on the folders. We have, for instance, mill 53, what is called the large and the narrow pore. So if you want, you can open these zip files and you see that essentially it's the same structure in the sense you have the cluster, inorganic clusters and the linkers are the same, but it is open pore or closed pore, like this, okay? And, well, it's over there also to highlight that if you compare experimental data that you have on the folder with a certain theoretical structure, you need to remember that this structure is for a certain, how to say, determination that you have done. In this case, the real material is a combination quite often of narrow and large pore. So there are some discrepancies also because of it. The other one is Richard already told you. You need to pay attention if your initial structure has water or other solvents inside, you need to remove it. You need sometimes to clean your collection. So if the structure deforms, some other potential terms may be needed or are needed to describe correctly the interaction, okay? And probably the most problematic one, because it is quite difficult to solve, is if reactions occur, okay? Reactions may occur because there is chemical absorption, okay? And in that case, we can probably solve or obviate this problem by adding some specific terms that are specific for that material and for that adsorbate, so they are not transferable as the ones that we will use in our exercises. And in some other cases, the only option is to use some more complicated methods based on the quantum mechanics. Before doing some hands-on exercises, we will not do this in class because this takes some time. Just to mention a problem that Moisés had in the past, okay, he performed experimental work and then he could not well understand the results. I will summarize very briefly the data here, if I have the right slide, because I think that I missed something. But basically, this is the one. Basically, I'm showing it for a material using Moisés found that when he absorbs, in fact this was done for ethane and ethylene, absorbs these gases in a model, in a structural model of a MOF, that was IRM of 8, and we then performed the calculations. We could not compute an isotherm, okay, that was matching the experimental line. As you can see, not only the calculated amount of methane is, in this material differed quite significantly, but also the shape of the isotherm. So something was not very clear, and the fact that it was that using the same computational setup for a very similar BOF, basically the difference is in the nature of the linkers, okay, that in this case is benzene and IR 8 is naphthalene, right? So very similar linkers. We could, as you can see, more or less, we could reproduce the experimental isotope. And, sorry, yeah, some slides are missing here. I don't know what happened. But basically, what we found by analyzing the literature is that the structure of this compound, in some cases, okay. So these are the organic nodes. These are the organic linkers. So lines are organic linkers. The spheres denote the inorganic nodes. Instead of crystallizing like this, okay, like in IR mod 1, okay, so the extended structure was like this. What happens is that another structure crystallizes in between the previous one. Okay, so in between the pores of materials, there was another structure that could grow inside of this. So it is called what is called the interpenetrated mold. And this is another problem that we found. Okay, so at the beginning we thought, oh, these calculations are rubbish; they cannot be employed. But after considering 100% crystalline model, we could more or less reproduce the experimental isotherm, which shows that if we have real good models, and if we have good knowledge of these C5s, the crystalline structures, even using these very simple approaches to compute the interactions between adsorbents and adsorbents, we can obtain interesting data. And basically now we would be moving to the pore laser exercise. No? Vivek, can you help me with this? So, pore laser requires, so if you have in your folder, you should have. I'm sorry because a couple of slides disappeared in the course of sending the data to Moisés. I don't know what happened. But basically what we will do now is to use a code that is named pore laser, as we saw before. Use the XYZ file that we produce, and we should move the XYZ. If you use another, you can download this for your laptop, otherwise you cannot execute this in Google, right? So you should download the pore laser working area. You can download everything that is on this folder. Yes. It's a very small tool. It's a very small tool. It's very simple to 400K. You can download it, and then inside you will find that okay, you have this executable and you have like working example. Yes. So in here you can put your XYZ file that you want, for instance for YO66, or for any other material that you have over there on the folder. So you can also open with the Vesta, you can open the Zeolite, you can open whatever you want.
and afterwards you need to, how to say, to tweak with this input data. This is probably what you're going to talk about.
Yes, note that in the case of the other material that we were talking about before, it was the more unique case, no?
Yes.
Note that we must remove
Yes.
with Vesta, there is some tools to delete the atoms that belong to the solvent, okay? So the pore must be empty.
And for instance, if you go for the morganite, you have already this Vesta. Yes, I already uploaded there. You in the morganite you already have a file extension Vesta where I already erased. Yeah, but it's easy to erase in Vesta. You just, how to say, select a couple of atoms and then press delete and they will go away. Okay? But you need to remember that if you are going to download zips from the web, yes, from databases, from the publications, quite often they supporting information you have zip files, yes. You need to remember when people are reporting this, are not reporting for you to do these calculations. They are reporting to accurately describe what they have found experimentally. Yes, this is the objective. And of course, if you are going to do some calculations with this, you need to remember that sometimes you need to arrange the data in the way you want. Okay? It's not because people are not reporting well the C files, it's because the C files should represent what they are measuring experimentally. And if they are measuring, density inside that is described by putting over there some oxygen atoms, they should report the oxygen atoms over there. Yes? Because otherwise they don't have a good fit between the zip file data they are reporting and the diffraction data.
Yeah.
Okay? It's just
in some other cases there are more other problems that are associated to this anisotropy that are found in some structures, but these are crystallographic issues that we will bring here.
I can eventually show just a very quick
Okay,
example
the other one.
of EPS.
So anisotropy, for instance, affects the structure of another material that was talked about Professor João Rocha yesterday, the titano-silicate, sodium titano-silicate structure.
So if
that presents anisotropy. So
if you
can you show the original?
Yeah, this is the original zip file. If you look in here, let me just view. So instead of representing one unit cell, I'm representing 2 by 3 by 3. Let's see what we get. So you see, if you rotate this,
make it a little bit larger, because it is very small on screen. In order to use this code, mouse is very useful because this this part is not.
You see, in here is the unit cell here, and then I extended to represent more. If you pick up the zip file for ETS 10, and this is from a good database, so it's not junk. So this is a zip file that is reported in a database for ETS 10. If you go and try to search for the pore, you don't have pore. You don't have pore. So if you remember the talk of Professor João talked about it, the problem is some of these have 0.5 probability of appearing. This is how crystallograms represent this. So the unit, some of these are appearing and some of these are not. So if you pick up this zip file and if you try to do some calculations with this, it'll give you what? No pores. And then we are measuring ETS 10 and you have porosity. So you need to remember a little bit about this what is the CIF file. What we can do actually is to do by hand, and of course with the justification that I just have given you, remembering that some of these.
Can you go back? Because the information about 0.5 was
Sorry. See.
just to show. The information comes in the
Yes,
okay,
yes,
this
yes.
is a long list, but as you can see, this oxygen 5, probability is at 0.5. So in half of the positions we have in fact an oxygen, in
And
half of them we don't have anything.
And in
That's
fact,
why some regions are
yes.
porous and some.
And in fact, you need to remove this, but also in a certain way that you respect, how to say, the valence of the atom. So if you start removing this, then you cannot remove this. Otherwise, you have some things in here that are not connected to anything. So if you start from this point, you remove this, but you don't remove this, and then you remove this, and then you need to either choose if you go on this direction or if you go in the zigzag. You have
Different polymorphs.
Yes. So for calculating porosity, forget about polymorphs.
Yeah,
What
these titanosilicate structures are difficult ones.
It's just
But I like that Moisés has already a
yes,
structure.
yes, just to highlight that. Okay, if you go and do the it's still not open. Okay.
Yeah, this is the right one.
Okay.
Now you can see what is the structure of ETS10 with the bonds, okay?
So if you remove this in a proper way, you just represent this polymorph, and then with this structure you can perform the calculation. So for us it's better to stay on the simple case. Nevertheless, we give you these cases for you to understand that if you go from theoretical structures or CIF file or whatever, you need to understand what you have. So I mean, in here you need to export the.
So let's start with the UIO66. So it is a simple one. IRMOF 1 is also an interesting structure. It's not shown here, but you can use it also for doing exercises. You need to copy the XYZ to the working directory.
So you need to copy here to the working directory. Yes. For instance, we just put this here.
We created a working example number 1, okay, directory, that basically you can copy there, drag and drop the C file.
So we are trying to do this. So you should copy and put it in here, and then probably what we should is going to talk about the input. Yes.
Yeah, we can start with input. This code requires some information because, as we saw before, when we transform from CIF to XYZ, we lost all the information about the representation of the unit cell. Okay, so in this file here, we must specify the name of the XYZ file. Okay, it should be UIO minus 66, and then the values of the A, B, and C vector. Since this is a cubic structure, we copy the same number 3 times, okay? And then alpha, beta, gamma, in this case, cubic structure, all angles are 90 degrees. Okay?
You can find these values in the raster, for instance.
You can find directly on the zip file as shown before, or in Vestra they appear. Keep going in here. No, but open. This is the right. Yeah, this is the right one. So no, peraí, it is not displaying that. You have to the X. Sorry. So when you open this, here the log region, you always have this. Yes. So in the case of this YO, it is 2744, no, and then 004. So we only need to go to that file and replace the values. So go here and so you should have like YO66, OIO666. Okay. So we can save this. Then if you go for the folder, yeah, there are some additional files. Okay, I will not enter in details, but for instance, this UFF.atoms, there is information about sigma II for some nuclei. Okay, I'm sure that zirconium should be there, oxygen should be there, carbon should be there, and because we are going to use probes like nitrogen and two, we have some information for nitrogen and helium inside. Okay, but basically the information is combined, as I explained before, with those combination rules. Okay, in order to obtain sigma and epsilon, which is information important for pore blade. Okay, the code runs something like this. Yeah. So the first column is sigma II, the second one is epsilon II, and the third one is the molar mass. You already have here a collection of the most common nuclei that you can find. Nevertheless, if you have a material with something that's not in here, you need to add it. Otherwise, the code will give an error because it will read the XYZ and then you have an element and it cannot read from this file. So it will not work. Okay, but you can add it here. Yeah. So the other file we can also show defaults, but we will keep it as lab said, okay, where is lab information. So this is the important one. Do not change these values unless you know what you are doing. Okay, so we collected already some good data, so don't change. For instance, we have here the sigma for helium. The epsilon for helium is already included here, so you don't need to touch it, okay? And for other nitrogen as well, the temperature. So if you want to obtain data at a different temperature, you can select a different temperature, but usually we use the default ones, okay? So we will not change this in this class as well. And there is another file that is the runbat. Can show it. So usually these files are not very well seen in Windows because they are used to spread viruses. Okay, because if you touch, it will execute this tool. But in this case, you can do it. It is proof already. It will work. So it will execute the portblazer.exe that is in the folder above, reads the input file. Okay, so this is the input data where we place the name of X, Y, Z, A, B, and C, and alpha, beta, gamma, and the results will be written to results.txt. If you don't use these, the results will appear in the screen, and as soon as you close the window, you will lose the data. So please leave this there. So in order to execute this, just double click on Windows, double click. So it will start. Even this calculation that is using a very simple model, just the Lennard-Jones potential to make calculations, it will take some time. Okay. So after some,
So you can try yourselves to see if you have problems, either with WIO or with another one. So it's going.
and as soon as this window closes, the calculation will be finished, results will be delivered to results.txt. Okay? Obviously, this depends on the speed of your processor. But is it a virtual machine working in 64 bits or 32?
Okay.
Because there are some.
Maybe it's because this is compiled for.
This is the ARM processor. Maybe you should talk with Marta, because ARM processors are a nightmare, okay? They are very good for people that is using artificial intelligence and so on. They are very quick, but most of the codes that were programmed for regular CPUs are not working in this ARM.
But it's not working.
Yeah, the Pro Laser can work.
Yeah,
Can work,
but Marta,
No, but it's not working in my virtual machine.
yeah, but you have to dig a lot, no, to tweak everything. Okay, but you may ask Marta, and she can tell how to do this. But so basically, we started with these files here, and now we have a lot of them. Okay. The most important one at this point, because we asked the code to write this, is the results. The results of txt. Okay, so is this working? Okay, so information comes to the screen. Okay, the name of the developer. They tell you to cite this paper and so on. And basically, after the first step is just to understand the volume of your systems. Okay, so this is very easy. The tool calculates the volume of the cell. In this case, a cubic one should be easy. Knows also because there is information. That's why in that UFF.atoms file they have written the molar masses. Okay, to understand the mass of this system. So we have an idea of the density and so on. So this is information that is calculated very easily, okay, without performing that Monte Carlo steps. And then now you have also information about the pore limiting diameter. So this all what is said here, I talked about it before. Okay, so when I showed the figures, the definitions are there. So for the limiting diameter in angstrom, the maximum pore diameter, and then some information that we can compare with experimental results. I will go immediately to the bottom of this.
Do you remember the value that you have for Do you remember the values that you have compared, that you have calculated? Yes? Yes? Do you need to remember that when you have values that it depends on how it is computed? So the values that we have below of volumes. For instance, in here, this is for helium. Then we have the value for probe. Can you go? Yeah, it's here. This is what you were talking about, yeah? Okay.
So these results are in centimeters per gram, but we have also some other units before, but we are almost ending this session. So let's move to the other part. I don't know how we can open the graphs here. Can we do this? I have the kitty grades. Yeah, do you have the grade code? You only need to drag and drop. I don't know if Excel can do this.
Para fazer
Para os gráficos.
este aqui.
Uhum.
Sim. So you have, for instance,
Okay, there is a tool that is named Qt Grace. It is a tool to process graphs. We only need to drag and drop.
so you can calculate, you can from here have the pore size distributions, for instance.
Yeah.
So you can also say just open this like this.
So drag and drop to Excel and then make the graph.
So you need just to so what you have is essentially these two things to plot.
Esse aí é o do integral.
É o integral
do outro.
Tá bem. Sorry, I opened the wrong one. So if you plot this, okay?
So you can have an idea of the pore size in this material, okay, and their distribution. Okay.
So you see,
So that is very useful information that you can extract and can play with it and can be compared directly with available experimental information. Always keeping in mind a few things. One, in this case, I think in the model we were neglecting some things, including the hydrogen atoms were not there. Okay, we have to add them to the XYZ file, they were not there. Another point is that the C file is for something that is 100% crystalline, and in the experimental sample, sometimes there are some defects, and this is very frequent in some kinds of families of materials. Metal organic frameworks suffer a lot of defects, big portions of the linkers that are not there, and pores are much larger than they should be. And
I think the important thing is with this tool, you can have a theoretical structure and then compare with your experimental data, and you can calculate also pore size distribution from the experimental data, pore, micropore volumes, and so on. And if you compare with these theoretical, let's call it theoretical calculations based, of course, on the crystalline model, if you have some mismatch, this can guide you for some problems that you have in your sample. For instance, one of the things that we noticed in this case of interpenetrated IRM of 8 is that when we apply this to the IRM of 8 non-interpenetrated, we have a very high surface area or micropore volume, and the experimental one was significantly lower. But the material was crystalline, and sometimes you cannot see interpenetration in diffraction, powder diffraction. It's very difficult because, how to say, they are in, how to say, the positions where you have the interpenetrated structure are quite often more or less the same in terms of symmetry, equivalent positions, so you don't distinguish easily in powder pattern. Yes? So, you see, sometimes it can give you some guidance for problems. If you have, for instance, higher surface area in your experimental data than what you can obtain from here, then it can mean, like Richard already said, you have defects where you have missing linkers, so bigger pores appear over there. Yes? So I think one important thing that we would want you to, how to say, take home is you have here two different approaches that in the end we cannot say, oh, this is the right one or this is the right one. Both are right, okay? Don't forget about trying to also say. The comparison of both things can give you information. Okay? This would be our most important thing. So you have experimental data and then you have some computational data. When things are not matching, try to search for, how to say, reasons. For instance, in here you see, if you look into this pore size, if you go for the Vesta and you try to look in the structure, you see that you have a cavity, a big one of tetrahedral cavity of this size, and one tetrahedral, well, several tetrahedral cavities of this size. So this is also, what to say, making some sense with the data, initial data. And maybe we can show the XY where we have the overlapping.
You have to, if you have it.
Yes, I think we have it, for instance. Yes, for instance, I just put here an example. Let me try to show this. And okay. Okay. You can pick up your XY of your material, XYZ, and then add more lines in the text editor, just copy paste the XYZ you have in here. For instance, let me see, we just finished, oh, sorry. Okay, so you have here, for instance, this probe occupiable volume, XYZ, which are the positions of your probe, nitrogen molecule. Yes. So if you join the two files, yes? Okay,
Don't forget to touch
the first line because you have 800 atoms and I don't know many more in here. And then you construct your XYZ and you can plot it in Vesta. And you can also see if this makes sense. It should make sense. And it makes sense, you have here the probes that are accumulating in the middle of the pores. Yes? This is the large pore of mil 53, large pore. The other one is much smaller. Yeah? Okay. And we are in on
So, any questions very briefly? I think we should add our email addresses to this PowerPoint file. So before we upload the PDF.
I think we have already a PDF there, but I will put another one.
And
we need what
if for some reason in the near future you feel some problems with this, or if you are interested in, even if you don't, if you have a material and you want to characterize it, maybe you can ask with that, you send him a sample, he can for sure perform some experiments, or you can try to get the lottery and buy all the equipment that are needed to do this. In the case of the computer, as you can see, it is a matter of knowing how to choose the right files. Okay, in order to make this quickly, we have several steps here that were very fast, but we must obtain, and this is critical, start from a very good crystallographic structure. We must know about at least something about crystallography. I don't know too much, but at least we must understand the concepts, okay? To understand this concept of anisotropy, where atoms should be there or not, because we must delete or not. The solvent molecules that are there, the addition of atoms that may be missing, because it is not always deleting, we may need to add some atoms.
And this takes time.
But after this, it is
More or less quickly.
with a laptop, these calculations are quite fast. The ones corresponding to this determination of the calculation of the isotherm, they took a longer time, but a long time, not very long, but they take some time. Maybe you can ask Marta about it, because she's calculating a lot of isotherms nowadays, so you can talk with her in the coffee breaks and so on. So that's it. No?
So we have now the poster session, both for the Department of Materials and Ceramic Engineering. So I hope you feel like coming, having a drink, some food. And I'm not sure if Richard and Moisés will join us, but
I don't know if I will try to
just for a small snack and a drink. Should be you are speaking for a long time.